Hello, my name is Liz, and this is my lab report for the first lab, which is focused on constant velocity. So the fundamental physical principles used in this lab are Newton's first and second law. So Newton's first law of inertia states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. And Newton's second law focuses on net force and momentum. So momentum is mass times velocity. And since the mass of the object we use in today's lab stays the same, it doesn't change, and we're studying constant velocity, that means that momentum will be unchanged. So because there is no change in momentum, net force is equal to zero. Essentially, when velocity is constant, net force will be equal to zero. The purpose of the lab is to observe the constant velocity of an object of our choosing and the resulting relationship between position and time. So after filming a video of me rolling an expo marker, I recorded the data using Tracker, and from the Tracker data, I created an observed model, and from the GlowScript source code, I created a predicted model. I compared those two models on Excel, and then I answered hypothetical questions at the end. Here is the video that I imported on Tracker. Using Tracker, I determined the start and end time, the initial position, the initial velocity, and the data points for position versus time. And I input all this data into GlowScript to create the computational or predicted model. In GlowScript, I changed the mass, the initial position, the initial velocity, the end time, the net force to zero, and the updated velocity and position equations that can be derived from Newton's second law. Here is the resulting video from GlowScript. As observed in the video, the object is moving in the positive x direction. Its slope for the position versus time graph is constant and positive. The slope of the velocity versus time graph is a straight line, and the coordinates for position and time have been calculated and are at the bottom of the page. Using this data from GlowScript as the computational or predicted model and the data from Tracker as the observed model, we can compare the two using Excel. So here are the predicted versus observed graph. The predicted model is the expectation. It is a perfectly linear graph with constant velocity. The observed model from Tracker is curved and it does not follow the path of the predicted graph, namely because of friction. Friction slowed the marker down. And as we know, due to Newton's first law, the marker's motion was changed due to this external frictional force. So net force is no longer zero. Another reason for the discrepancies between these two graphs is that the expo marker is not perfectly circular in shape. And as you can see, around 0.125 seconds is where the observed model begins to diverge from the predicted model. So two ways I could have fixed this. Cutting the video earlier before the marker started to slow would have helped me capture its constant velocity more. And if I were more careful when tracking the position of the expo marker in Tracker, if I were a bit more meticulous, my data would have matched the predicted data better as well. How would this lab be different if I were to flip the axes so that the positive x and the negative x were interchanged? Well, the answer to that is that the graph would be reflected across the x-axis, resulting in a negative slope, which I tried to show in the picture here. The velocity, however, would still be the same. So, would it be possible to calculate exactly how many pushes and pulls, essentially forces, were in action to make the net force equal to zero? The answer to that is no, it's not possible to do that using only Newton's second law. But using Newton's second law, we can make the general statement that we know that momentum and friction played a role in the expo marker's net forces. In conclusion, Newton's first and second laws helped explain the behavior of an object. When an object's net force is equal to zero, it does not necessarily mean the object is stationary. It could just be at a constant velocity. The differences between the predicted and observed models can be attributed to human error and outside forces, namely friction. Thank you.